Okay, so in the last class we discussed the NPN transistor. So we'll discuss the function of a PNP transistor, and here you can see the circuit symbol. So in PNP, the arrow should in the circuit symbol arrow should point towards the base because it's always P to N, right? So if it's PNP, then the arrow is from P to N. Okay. So PNP. Okay. And as we discussed in the NPN transistor, PNP transistor also in the emitter, the doping concentration is high, okay, compared to the collector terminal. So we have two p-type semiconductors, right? And in the middle n-type semiconductor, if you consider these p-type and this p-type, this one emitter has a large doping concentration compared to the collector, okay? And also the BC junction BE junction should always forward biased. BE junction, BE, this one should forward biased. BE junction should forward biased, and BC junction should reverse biased. You can see here, this is P type and this is N type. So here the positive terminal is connected to P and then negative terminal connected to N. So then this is forward biased. PE junction is forward biased, and here the BC junction is reverse biased because the positive terminal is connected to N side and the negative side is connected to P side. So reverse biased. Now, if you consider the NPN transistor, here also you can find that BE junction. So BE junction is forward biased, and here BC junction is reverse biased. Okay, so you can note down these 3 points. So one point is the doping concentration in emitter is higher than that of the collector. Okay. The doping concentration in emitter is greater than the collector. The doping concentration of emitter is higher than that of the collector. And second point, BE junction is forward biased with a small voltage. We need only a small voltage with a small voltage. And BC junction is reverse biased. With a large voltage. DC junction is reverse bias with a large voltage. So this is the same, these 3 points are same for all, for NPN and PNP. For both, this is true. For both NPN and PNP, this has to be correct. Okay. Okay. You can note down this. So in emitter side, the semiconductor is highly doped than collector, And then BE junction is always forward bias with a small voltage. BC junction is reverse bias with a large voltage. So for NPN transistor also, for both NPN and PNP, this equation is true. IE, the emitter current, is equals to IB plus IC. Okay. And also IB is very small compared to IC. So you can see this here a small current, here a large current. And the total current is IE. So this side is IE equals IC plus IB. Okay, so you can write down all of these under the NPN transistor. So the circuit symbol is this, and then this is the simplified circuit. This is the construction. Like we can use P-type, N-type, and P-type. Two P-type sandwiched N-type semiconductor is sandwiched between two P-type semiconductors to make a PNP transistor. And here emitter has a high doping concentration than the collector. So here this is the circuit, simplified circuit. This using the symbol. Okay, guys, you can take a screenshot so that you can draw and complete that later. So here the key things are here this BC junction is reverse biased and BE junction is forward biased. Okay. So let's just go through this quickly. The emitter of a PNP BJT, that means bipolar junction transistor, is made with a high doping ratio. So emitter, you can see emitter has a high doping ratio, right? So that's very important. The collector with a moderate doping ratio, the collector has a moderate, that means a low doping ratio, and the base with a very low doping ratio. Okay. When a switch is individually closed, no current flows in the circuit as it does not complete closed circuit. When a switch is individually closed, okay. If you close only one switch, it doesn't make current. So here, if you close only this, then there won't be any close path for a current to flow. So, or else if you close only this, then also there won't be any closed path for the current to flow, right? Okay, that's what it means. When S2 and S3 are close together, BE junction is getting forward bias, yet it makes a very weak current due to the low doping ratio of the base. So S2 and S3. So you can see here S2 and S3. If you close S2 and S3, there will be a small current because of the low doping concentration of the base. When S1 and S2 are close together, BC junction is getting reverse bias, therefore no current. will flow in the closed loop. We studied under the PN junction. When the PN junction is reverse bias, there will be no current, but there will be very micro ampere, very leak current will be there. So due to that leak current, what happened? The depletion region will get wider. Only that thing will happen. But when all three switches are close together, then electron who are highly pressurized to go to base can now directly jump from emitter to collector, as there is a deficit of electrons in the collector due to its reverse biasing. As a result of this, current of milliampere range will go from collector to emitter, while very small microampere range current travels from base to emitter. With this, we can conclude that in order to make a BJT work properly, the BE junction should be forward biased, BC must be reverse biased. So you have to highlight this. So the BE junction should be forward biased and BC junction must be reverse biased. And also the emitter of BJT made with high doping ratio, the collector with a moderate ratio, and the base with a very low ratio. Because these points you will be asked in MCQs. When you practice in past paper question, you can find out. They will ask like whether true or false statements. They will ask these questions. So the highlighted parts are very important. The other things you can write it down. I'll give you a minute. So it's I can be NPN or PNP. These two things must satisfy emitter of BJT, bipolar junction transistor. So either NPN or PNP is with a high doping ratio, emitter is high doping ratio, and collector moderate doping ratio, and base is very low doping ratio. And BE junction should be forward biased. It can be NPN or PNP. BE junction must be forward biased, and BC junction must be reverse biased. Sidra, can you hear me? And how about the audio call with the mic? It's
Yes,
better,
I
right?
can hear.
Chat box. Guys, can you please drop a feedback regarding the audio quality? Guys, I'm expecting reply from you. Please stop message. And I hope you are aware if I'm connected to this, I won't be able to send you out that there is no speaker now. Uzman, can you hear me? I'm not getting any response from anyone.
Yes, I can hear you.
Yes.
I can hear you, sir.
Guys, can you hear me?
Yes, sir.
Okay, thank you. Okay, and by the way, yesterday I called and checked with one of my friend who is working at Dialog. He said that there is a integration with Airtel because I think Dialog has purchased the Airtel. So because of that only provision was there yesterday. Anyway, now I think now it's totally fine. It's worked so well. I know it should be. Right. So if you're still writing, you can take a screenshot, but these highlighted are the most important facts. Okay, so let's move on to the next part. Uh, so here PNP also emitter is made of high doping ratio, collector moderate, and the base with very low doping ratio. And the BE junction should be forward bias and BC be reverse bias. I think by mistakenly I was showing you the description of the NPN one. So this is the PNP one. So you can see it's almost similar, but only the structure change. But NPN or PNP, the emitter should have large doping concentration, collector moderate doping concentration, and base very low doping concentration. And the BE junction should be forward biased and DC junction is the reverse biased. Okay, so here you can see the uh, circuit symbol of two NPN and PN transistors. So this is NPN. So it's pointing from P to N, and this is PNP. So here arrow is pointing from P to N, and current is always from P to N. So you should be able to mark these currents properly. Now this is P and this is N. Therefore, current will flow from this P to N. Therefore, the current will be in this direction. So once you mark IE, then you can straight away mark IC and ID because both these two should come in so that the IE equals to IB plus IC. Here the same. So if the current here P to N, P, so IE will be in this direction. Therefore, IB and IC also will be this direction because total current coming in should equal to total current going out. So IE is equals to IB plus IC. So both transistors emitter current is equals to the base current plus collector current, and base current is IB is very small compared to IC. So most of the case we in calculations we take IE is approximately equal to IC. That means we are considering IB is negligible. IB is approximately equal to 0. Right? So if you make this term 0, then IE is equals to IC. Okay. You can quickly draw down this. So remember in a PN, in transistor the current flow from P to N. I mean you had to consider the BE junction. So consider the BE junction and the arrow. So the arrow will indicate directly the direction of the current. So here P N, P N, P, and this is N, P, N. Again current is flowing from P to N. Here P to N. Okay, so there are three configurations of a transistor. So when a transistor used in a circuit as a signal amplifier, there is always an input and output side of a transistor. One terminal acts as an input circuit or input terminal, another acts as a output terminal as the uh, and the remaining terminal as the common terminal. So there are three terminals, right? Uh, Collector, emitter, and base. So if one terminal acts as the output, the other one acts as the input, then the remaining terminal acts as the common terminal. That is, it is common to both. You can see can describe as input circuit and output circuit. So this remaining terminal is common to both input and output circuit. So we can consider that as a common terminal. Based on the selection of common terminal, there are three types of transistor configurations: common emitter configuration, common base configuration, common collector configuration. So write down the topic configurations of a transistor. Write down the topic configurations of configuration of transistor. So write down under that three. There are three types of transistor based on the selection of the common terminal. There are of the common terminal. So first one, common emitter configuration, common base configuration, common collector configuration. Okay, and then write down a subtopic. Now we are going to discuss each of these: common emitter configuration, common base configuration, common collector configuration. But in order to discuss this, we need to give supply energy. Now it can be like common emitter configuration, but we want to first bias the transistor, right? Now we discuss about biasing a junction, PN junction or a diode. So biasing means you are applying a giving a voltage. So here also we have to give a voltage supplied to the transistor to power the circuit, right? So if you power only, we can discuss what is common emitter configuration, what is a common base configuration, what is common collector configuration. So write down a subtopic as biasing a transistor. Okay, so write down under that, supplying energy to transistor to make it work properly to get the desired output for a given input is known as biasing a transistor. So write that sentence. Okay, supplying energy to the transistor to make it work properly to get the desired output for a given input is known as biasing of a transistor. Okay, so biasing transistor mainly uh, can be done in two ways. Mainly biasing of transistor can be done in two ways. One is base resistor method, the other one is potential divider method. Mainly biasing of transistor can be done in two ways: base resistor method, potential divider. Write down. So now first we will discuss transistor configurations. So I will first start with common base because that's the circuit that we discuss in both NPN and PN transistor. So therefore we will first discuss common base configuration. So write down the topic common base configuration. So in biasing, there are two requirements. So you had to make it uh, BE junction forward biased and BC junction reverse biased, right? That's I'm repeating over and over. Right? If you want to bias a transistor, first thing you want to forward bias the BE junction, reverse bias the BC junction, and there should be a input resistor for the uh, input circuit. So we can consider this as the input circuit and this is the output circuit. And there's a, to take the output, you have to put a output resistor. So now if you want to bias this transistor under the common base configuration, you want to forward bias the PE junction, reverse bias the BC junction, and you have to put resistors in the input circuit and give the input. There should be a input resistor and take the output. There should be a output resistor. Right now, for example, this RE can be the resistance of. Now, let's say you are connecting to a voltage supply, for example, alternative signal. So it might have some resistance. So it's resistance, and then RC. will be, for example, let's say, for example, it's connected to radio. Okay, okay, so it's connected to the radio. So the resistance of the radio is then RC, something like that. Okay, so you can draw this circuit. You should be able to draw the circuit completely without looking, right? Now, okay, I'll tell you how to draw that without looking the circuit, because it's all based on the logic, right? First, you have to take, now let's say, common base configuration. First, you have to think you are using an NPN transistor or PN transistor. So you can start with the transistor. And okay, first you draw the circuit, and then I'll explain you how to construct the entire circuit based on the logic. Logic means not the logic gates. I mean, තර්ක තර්ක මත අපිට මේ circuit එක ගොඩනගන්න. Raise your hand if you finish drawing the figure. Also mark V input and V out. That is marked there as color. So in common base configuration, base is the common terminal for both input and output. So here this one you can consider as input circuit. So this is input and this is output circuit. Draw කරලා ඉවර නම් done කියලා message එකක්. Okay, I'll explain you how to construct this based on the right. So let's say you are considering NPN transistor. So let's consider PN. So NPN means P to N side. So this is collector is emitter. So this is NPN transistor. NPN transistor. Okay. So then what we want to want to make the BE junction forward bias. BE junction forward bias. So forward bias. Forward bias. And then BC junction should be reverse bias. So this N. Okay. And then there should be a resistance for the R output. The R out. This resistance for the input R out. So we usually consider the B terminal as the input. and this is out. Okay, actually I should have drawn this in this way. I'm taking the circuit, and here the B, and this side is emitter. Take the emitter terminal side and collect terminal this side, because uh, this is totally correct. It's not wrong, but as a convention, our normal thing, we take the input as this side and take the input this side and process with like input process output. No? So that's how you usually do, right? So by considering that, normally you have to draw taking the emitter term to this side. B, and here BE junction should be forward biased, and then C junction should be reverse biased, and there should be a resistance to take the output, and here a resistance to give it. That's all. Now suppose, let's say you want to construct this for PNP transistor. Still you can do it. PNP. So emitter, base, collector, PNP. So arrow is in. Here you have to mark the current as well, otherwise the circuit is complete. That means you have to mark I. Here IE, in this side it's IB, and here IC. Okay, now it's come. So now here, now we take PNP transistor. The PNP transistor, first you have to draw the PNP transistor, PNP star. And the configuration is common base, so you have to take the base at the middle. Okay. So then what we have to do, BE junction should be forward bias. BE junction should be forward bias. And then BC junction should be reverse bias. P and one should be reversed. And then to give the input as resistor, so you can mark RI, or it's in the emitter terminal, you can mark RE also. Totally fine. Or you can here then for the take the output RC resistor. Okay. So now we can mark the current. Current is always here from P to N. So here IP is side. So here IP and here IC. I mark the current here also. So IE equals IB plus IC. Did you understand? So if you study the basic things, you can draw this. These are the basic, like BE junction should be forward bias, BC junction should be reverse bias, and then there should be a resistor in the input circuit to give the resistor. There should be a resistor in the output circuit to give the resistor. And the current, we know always IE is equals to IB plus IC, right? So these things, with using these fundamentals, we can construct the circuit. Now we have done for the common base control. Likewise, with the same logic, same fundamental uh, principles, we can construct the circuit for common emitter configuration, common collector configuration. We will see that soon. Okay. So you should be able to draw this, right? If in exam, if they ask you to draw the circuit, then you should be able. It's not hard. It's only you understand the. I mean, you don't need to memorize the circuit. they had to understand the facts, like what should be done. Okay. So then the circuit is done, and then the voltage across RE here, the input resistance, uh, is the V input, voltage input, and this the V out. Okay. So here we can discuss something called voltage gain. So how much of voltage can be obtained here? So voltage gain we usually mark as AV. Right? So voltage gain, okay, voltage gain is equals to output voltage V out divided by V input. The output is, we can use Ohm's law for this resistor is ICRC divided by input is IR. Okay. So this is the uh, voltage gain. So if you want to get a good output, the RC should be greater than R, right? If you want to take a large value, because we know IE, IC and IE approximately equal to 1. This one, because we know IE equals to IB plus IC, and IB is very small, therefore approximately equal to IC, and also it's very close, and also IE is greater than IC, right? Now, for example, IE can be 25 ampere, right? IE is, let's say, 25 ampere. I'm just saying this is not the exact for values, but I'm just saying to give the idea of comparison. Then this, let's say, IE, then I see something like 24.99, 24.9997 amp, because IB is in the microampere range, right? So some take for 2 decimal place, 997 amp. Okay. So you want to take a good voltage gain RC, you can increase the value of RC compared to R. Okay. So that's the voltage gain. And then current gain we can write is, current gain is, here we take alpha, output current, I output, that means output current is current to RC IC divided by I. So this is approximately equal to 1, right? Because they are more like same. And then the output, power output, the power gain, the power gain we can write equals to V out into I out divided by V in into I in. So V out is equals to ICRC, ICRC times V I out is IC, and then V input is IERE times IE. So here we can write IC squared RC divided by IE squared R. So therefore, the power of gain is equals to so IC over IE is approximately equal to 1. So therefore, if it, so power gain, you can first write down this equation IC squared RC divided by IE squared RE. So then we know that this we can write like this E equals IC over IE squared times RC over RE. So we know IC over IE is approximately equal to 1. Therefore, our gain is approximately equal to RC over R. So if you use a large output resistor compared to the input resistor, you get a good power. Okay, is that clear? Okay, so you can write this down. Now, this is actually, we have derived this current gain, voltage gain, power gain for NPN transistor. If you do that, so for PNP transistor, you get the same. You get the same voltage gain, power gain, and current. Okay, so I will give you a homework. You have to draw the circuit for PNP transistor and then obtain this voltage gain, power gain, and current. Okay, that you have to do. You have to practice. In case you got in the exam, you should do right. So therefore, you can practice now without looking the note. Okay, you have to consider common base configuration PNP transistor. Sorry, NPN transistor. This is for PNP. No, sorry, this NPN, NPN. So P to N. So therefore, you have to do it the same for PNP transistor. Okay, so you have to draw the circuit and get the voltage gain, power gain, gain. So first you have to get the voltage gain and current gain, then you can get the power gain. So here one more thing I'll tell you. Because, have you finished writing this? Really, Virudha? I can use this place. So here the power gain actually what is equals to V out over V in, V out over V in times I out over I in. Okay. So this one we can write V out over V in is voltage gain. So this is equals to AV times this is alpha. So E equals voltage gain into current gain. So power gain is equals to voltage gain into current gain. Okay, that also note down. It's easy. Normally how do we calculate the power? Power equals VI. So likewise, power gain is equals to voltage gain times current. Okay, and then one last thing about this circuit that we have to understand, whether the output signal is inverting or non-inverting. That means if you give an input to the input circuit, so the output, you have to find whether it's inverting or non-inverting. So inverting means there will be 185 phase change, 180 phase change, 5 in radian 5 phase change. So non-inverting means there is no change in phase. So that thing now this one this how do we find that actually? So when I was learning, for me I just when the teacher was taught me just said like for this common base configuration, the output signal is non-inverting, right? But with my practice by doing questions and all, I realized there is a way of getting and identifying whether the signal is inverting or not, right? So for that, what you can do is simply now this is the input and this is output. Then you have to draw a path, closed path connecting the input and output. So I can draw this closed path, right? That connecting the input signal and output signal. And in this closed path, you check the direction of the currents, right? In this closed path, you have to check the direction of the current. So here the current is going in this direction. So here this one also, I see also going this direction, the same direction of the loop. So here the current is moving this way and here the current is moving this way. That means if you consider this loop, in this loop, it is moving in the same direction. The current is moving in the same direction. Uh, therefore, the signal is non-inverting. So you can write the output signal is non-inverting. Output signal is non-inverting. Okay. So what you can do is again I'll explain now. This is the input and this is the output. So you have to consider a closed loop that connecting the both input and output. So in this closed loop, the current is flowing in the same direction through the input resistor and output resistor. Then the signal is non-inverting. So you will see if the signal is inverting, how it looks like. We will see that because we have other configuration source and a command emitter command collector. No. So that's all. And please, as I told you, you have to complete the same note for PNP transistor in the common base configuration. Under the common base configuration, you have to consider the PNP transistor and mark the currents and get the voltage gain, power gain, and check whether the signal is non-inverting or not. So there also you will get the same current gain, same alpha, same voltage gain, same power gain, and also the output signal is non-inverting. You have to do it and see, okay? Maybe right after the class also, fine. That's must you had. So only these are the facts that you have to learn in this, okay? So if you study the electronics properly, it is where you can take marks easily. Now, when I was doing my A levels, the first question that I will choose and I pray is magnetic field, because magnetic field questions are very easy, because those who are making the papers, they think magnetic fields are difficult for students, so they think they will don't give complicated questions from magnetic field. So therefore I always wish for magnetic fields question to be there, because sometimes magnetic questions are optional. It will be there in 1 year, it won't be there in another year. But if you are getting magnetic field means, that's much easy. And then you have to do one question whether from its current current dynamics or electronics, right? So or both will come under the same question. One A part will simple A part uh, current electricity, and the B part comes in electronics. So electronics is also very easy questions that you can get marks. Okay. Because when it comes to mechanics, the thing is they will give questions the students to think. මෙහෙම આવත් මොකක්ද? You had to think the consequence. You had to have a knowledge what would happen. They will give questions like you had to think. But like magnetic fields and gravitation field, electronics, these are the solid theories. Very questions are very straightforward. Okay, so let's move on to the next part. Let's do the common emitter configuration. So write down the topic, common emitter configuration. Okay, so let's try to draw the circuit without looking. Okay, so here we have to take the common emitter configuration. So let's first consider a NPN or PNP. You can consider. Let's take PNP. Okay, PNP transistor. So this should be a PNP transistor common emitter configuration. So I draw the transistor. So here I take the terminal E, that is should be the common for both input and output. So left side you can consider the input circuit, right side output circuit. So the common is emitter. So we draw this transistor, and at the middle emitter terminal will be, and then we complete the transistor. So P and P. So P to N. The arrow should be pointing. Yeah, P and P to N. And then this. So here the base, right? Base is the common to both. I mean, in the middle, won't change. So this will be automatically what collect. So then I can complete the circuit. So we know BE junction should be forward bias. BE junction should be forward bias. Okay. And then this this junction, CE junction should be reverse bias. the other junction should be reverse bias. PN. So this side we have the okay. So usually uh, the for the collector terminal we put the large voltage, right? Voltage. So then we done this. So current is from this direction, so I can mark IE, and this is therefore this direction IE. So here downward IC should. Okay. So our battery terminal also push the current, and then we had to put resistors for the input RE, and for the output. So the current for the IC is RC. Okay. So here E is the common, so therefore I is the common current. So IB should be the current through the input, IC should be the current through the output. Okay. So this is the circuit. That's all. Okay, now let's try to draw for NPN transistor. NPN transistor. So you take the transistor first, the common is emitter. You write the emitter. So H is, and then this NPN, the arrow will be displayed. And here the base, and BE junction should be uh, forward bias PN. So BE, so should be forward bias. And then this junction should be reverse bias. So here PN, PN, so reverse bias is P, so it has the negative term here. And this C, and let's mark the current. Here current is this direction, so IP, the IB, and IC. And to give the input RB, input resistor, and the output resistor RC. Okay. Yeah, now done. So that's all. It's very simple drawing the circuit. So first thing you have to find which configuration common emitter, and then you have to see which type of transistor is PNP or NPN. PNP means then you have to write this, and then accordingly you can construct the circuit. And the circuit first thing, BE junction should be forward bias, and CE junction should be reverse bias. It should be reverse bias, and then you have to put a resistor for the input, resistor for the output, and then you can mark the current accordingly. Okay. Okay. Do you find drawing these circuits are easy? Yes. Say yes. Do you find drawing these circuits are easy? Is it easy to draw? Come on, guys. You have to respond. Not only it gives me a satisfaction. Okay, the student is there and seen and studying. Otherwise, I won't. I would. Get. I'm not. What do you say? Satisfied. Now there is a sir. I mean, combined maths sir Manoj Solangar. He strictly wants everyone to turn on the video because otherwise, as a teacher, we won't get the satisfaction if the student didn't understand or if the student is not there. We want to know what happening behind the screen. So please interact with the class. Call am I? Chitra, are you there? Yes. And Usman, I would appreciate if you keep continuing interacting with the class. If I ask you a question, you have to be quickly put the answer, or just at least raise your hand. If I ask you, did you understand? You can just raise your hand so that okay, you understood that. You have to interact with the class so it gives satisfaction. Okay. You will ඔයාට ඒක තේරෙන්නේ if you become a teacher and if you are doing the class and if the students are there, you will feel how it feels like. Otherwise, මම කියන දේවල් like it will be like බොළඳ විදියට තියෙන්නේ. But if you stay here, then you will realize how it feels. Anyway, so I hope you understood. So then now let's discuss the voltage gain, current gain, and the output signals, those things. Okay. So first, voltage gain or the current gain. So the current gain is so here output current is IC over IB. Now we know IB is very small, right? Uh, so IC is a current in the milliampere range, and IB is a current in the microampere range. That means the IC is 1000 times greater than the IB, approximately equal to 1000 IB. Okay. So therefore, the beta is very large. So here beta is the current gain in common emitter condition. So therefore, now for example, let's say if you want to amplify a current, so you can use this common emitter configuration, right? So for example, let's say we have a input signal. Okay, for example, we can consider a speaker, right? So speaker, what does it take the input signal and then amplify the current and it gives a large output, right? So there we can use common emitter configuration. Right? So this we can use as signal amplifiers. Common emitter configuration we can use as signal amplifiers. Okay. So beta is ICO IB since IC is very large compared since IB is very small compared to IC. So therefore this will be very large. Beta is very large, greater than 1. Right? Something around 200, 100. Beta can have such values 300. Okay. And then voltage gain is V output over V input. So V output we can write as so AV equals to V out over V input. So V output is RC IC over RD IB. So IC of IB is beta, the current gain. So beta times RC over R. So this is the voltage gain. Okay. And then you can calculate the power gain. So power gain is V output into VI in output over V input over I input, right? Because V output, power output is equals to V out into I out. So input power, output power divided by input power. So then this is equals to V out over V in is, we know, V out over V in is AV, right? So this AV times beta. So AV is, we can write beta times RC over RP times beta. Therefore the power gain, we can write beta squared times RC over RB. So even you can consider the RC and RB are same value, let's say 5 ohm, 5 ohm. But still, again, there will be a beta is large. The current is amplified, so beta is very large. So there is a good power uh, gain. There is good power gain, common emitter because it's beta square. So let's say if beta is in the order of 100, so power gain will be in the order of 10,000. Okay, so write down this quickly. Okay, so and again I'll give you homework. Now this is the circuit and current gain, voltage gain, power for common emitter configuration in NPN. So this is for the NPN. So the same thing you have to do for PN. Okay? You have to complete it for PNP transistor under the common emitter configuration. Okay. So and the last thing, now here you want to find whether the signal is inverted or not. Okay, right? So for that, as I told you, කරන්න තියෙන දේ මෙච්චර simple. You had to find the input. So this is the input and this is the output. So input එකයි output එකයි connect කරන විදියට single loop complete circuit එකක් you had to consider. You had to consider a complete circuit connecting the input and output. So I can draw like this. Okay. So here, if you consider the current in this loop, through the RB, it's going this direction. So may current but through RC, it's not in this direction. If it's also going in this direction, then signal is non-inverting. But we can see the IC is in the opposite direction. Therefore, current through the RC is in this direction. Therefore, here the signal is inverting. The output signal is inverting. So if you study in this way, then you don't need to memorize. Common base නම් non-inverting, common emitter නම් inverting කියලා කටපාඩම් කරන්න. ඈ එක්සෑම් එකේදී ඔයාට මෙන්න මේ සර්කිට් එක තියෙනවා. සර්කිට් එක ඔළුවේ හිතා ගන්න පුළුවන් වෙන්න ඕන. හරිද? හොඳට ගණන් හදලා ගානම් අනිවාර්යයෙන්ම මේක පුළුවන්. Okay, anyway, then you know that fact. You can draw like this and then know. So here the current is this direction, this direction. So therefore signal is here output signal is inverting. Output signal is inverting. That means 180 phase change. Okay, so if you consider the command base configuration, we can use that for more like for switch, right? For like a switch, there's if we bias the C function, then there will be current in the if we bias the input circuit only, then we can get current in the output circuit, right? So it's like we can use for like, but for this one common emitter configuration, we can use for signal amplifiers. Like for example, if you want to amplify the sound, if you want to increase the intensity of the light bulb, uh, so you can use this for like amplifiers. You can amplify the signal. Okay, so some students will understand misconcept that here we give a small current and get a large current. So it's like violating the energy conservation. How it is possible? Because this is not violating any energy conservation. We can see the output circuit is powered by a large battery, right? It has a large power source. So only we are controlling by the control the output circuit by the input circuit. If we bias this circuit only, we have a current in the output circuit. Otherwise, there won't be a current. Okay, so then we can move on to the next. If you're still drawing, you can take a screenshot. I mean, just writing, you can take a screenshot. And finally, common collector configuration. Okay, so I will give you the opportunity to draw the common collector configuration for, let's say, NPN transistor. Draw the common collector configuration for NPN transistor. You have to draw and send it to me. Okay, you can send it to the Zoom chat, or else you can WhatsApp me. If you're unable to, when you're sending through Zoom chat, send it to the Knowledge Institute, not to the Rimaz. Don't take much time. So now first thing you have to consider the collector is common. So you have to take collector common term, and the transistor is NPN. So you have to mark the transistor accordingly term. And then you have to draw the input circuit and output circuit. And then you have to see which terminals we have to forward bias, one to reverse bias. And then for the input, to give an input, there should be input resistor. Take the output, there should be output resistor. Okay, quickly draw this. Are you done? You guys need more time? අනිවාර්යෙන් සතියට එක පාස් පේපරයක් කම්ප්ලීට්ලි කරලා එක තමන්ම ඩිස්කස් කරන්න. Then you will find out what are the things that you need to cover, right? Polish කරන්න ඕනේ. Basically, you have to, and you can do self evaluation. And when you are doing this main, especially for MCQ paper, you are doing, you have to keep time, and it's very important that you have to answer the question with means for each minute, or you get question, you get only 2.4 minutes. So that means 2 minutes and 40. So therefore, each question you have to finish at least by 2 minutes. Each question you have to do it by 2 minutes. When you are doing MCQ paper exam, if you realize, okay, this question is hard, it takes more than 2 minutes or more than 2.5 minutes. So you have to skip that question and move on to the next question. ටග්ගාල හදාගන්න පුළුවන් ප්‍රශ්න ටික මුලින්ම කරගෙන ඇයි කිව්වනේ දැන් ඔයා අමාරු ප්‍රශ්නයකට ඔයා වැඩි වෙලාවක් ගත්තා නම් කරන්න පුළුවන් හොඳට ලකුණු ගන්න පුළුවන් ප්‍රශ්න මග හැරෙන්න. So you will miss those marks that you can get. Right? So therefore, if you find out that question is difficult, it will take more than 1 minutes. At the instant, if it can, I දෙසරක් හිතන්න එපා. ඔයාට එහෙම දෙසරක් හිතුණාද? හිත කරලා ඊළඟ question එකට යනවා. ඊළඟ question එක කරලා සම්පූර්ණ paper එක ඉස්සරහට පස්සේ, and then in the next round you can catch up those questions. So that's the way you have to see. Otherwise, if you spend much time like ප්‍රශ්නයට විනාඩි 5ක් ගන්නවා කියන්නේ ඒක ප්‍රශ්න 3ක් කරන්න පුළුවන් කාලය. හරිද? ඒ හින්දා you have to spend at least maximum 2 minutes per question. I think that's it. So here, common collector, and input is space, and then first thing, each the input set one has to be forward bias. So it's forward bias, and this one has to be reverse bias. So here enter, for the enter plus, so it's uh, forward bias, and then collector is the common. So you have to consider the here emitter. So here emitter inside has to be reverse bias. So here the polarity of this has to be and the resistance you have to put here. And then RC, actually it has drawn this figure in the upside down. කියන්නේ අඳලා තියෙන එක කිසිම වැරද්දක් නැහැ. දැන් මම සාමාන්‍ය explain කරපු ක්‍රමයට උඩ now I will draw this here. So first we want to take the transistor and then the common collector. So this C right here. And then always the base will be in the middle, and then therefore this is E and this is B. So NPN, right? We are talking about here one more main problem, we haven't marked indicate the arrow. We have to show that this is a NPN transistor or PNP transistor. So ඒක නැත්තම් මේ සම්පූර්ණයෙන් කොච්චර ඇන්දත් හරියන්නේ වැරදි. That's a big mistake. You have to indicate the uh, direction. So here NPN, so it has to put this. Okay. So then we can take the common collector is here, and then this is the input circuit. So here this should be forward bias. PN. And then this has to be reverse bias. So here N, the N plus. And here resistance RP, and here the resistance RP. You can, if you want, you can mark the resistance here also, that's totally fine. You can mark here the resistance, or if you want, you can mark here the resistance, that's totally fine. RE. And then currents we have marked. Sorry, I made a mistake. Here we have to so I had to mark the arrow here, not in the collector. So always from base to emitter, and therefore the direction of the current is this IE, and here this is IC, and this is IB. So you haven't marked the currents also, that is also must. Okay, you have to mark the currents, and your marking resistance is wrong. Only one is not enough. You have to, the resistance you can mark either, you can put the square this one, okay, or else you have to put zigzag. Okay, so this is not enough for the resistor, so you have to please correct this. Okay, so therefore this is the circuit in common collector. Okay, so here make confused because the shape is different, but it is exactly the same for what I have drawn. I show you. I'll explain you. So these two circuits are the same. Okay, so here uh, you can see here IE, but I have taken the other side, this side, and IC is here. No, I think this one is wrong. I think, yeah, here this is common emitter. Mm, no, this is common collector. I think so. This is the common collector. So collector terminal has to be common. So please draw the circuit which I have drawn. You can draw this circuit, right? Because this is we have here is common emitter. We have taken common. So that is, so it's wrong. You have to draw this. So draw this circuit. Raise your hand if you are done with the drawing part. Okay, so here the current gain is output current divided by input current. Output current is current through the output is IE, current through the input is IB. So IE of IB, we know IE is greater than IB. So therefore, current gain is large. Okay? Current gain is large. And then voltage gain. So voltage gain is, we know, output voltage divided by voltage. So output voltage is, so here we can use V out for IERE, the Ohm's law, and IBRB. So here also we can get a good voltage gain, and power gain is given by V out over V out into I out divided by V into I in. The power gain I can write V is equals to V out over V in. That's the voltage gain is IE out divided by IB RB times IE IE over IB. So therefore it is equals to IE over IB whole thing squared into RE over R. So in this common collector also we can get a large power gain. Though in common collector we can get a large power gain, but still we go with common emitter configuration for amplifiers, signal amplifiers. Okay. So here there is no phase change, because now here you can consider this uh, this loop. So in this loop, the current through RB and RE are in the same direction, so no phase change. No, so output signal is non-inverting. There is no change in the phase. Okay. If you want to be expertise in electronics, electronic lesson is not so hard. What you can do is study the theories uh, very well and practice some questions and try to teach one of your friends, right? So then you will be very confident with the electronics. අර අපි ඉගෙන ගන්නකට වඩා අපි කියලා දුන්නාම අපිට ඒ ලෙසන් එක ගැන confident එක අපි එයාට කියලා දෙන්න කලින් අපි හදාගන්න. So this electronics is very easy if you study it properly. Okay. Right. So then write down the topic, biasing a transistor. Biasing a transistor using a single voltage source. Okay. Getting a transistor to its normal working condition is known as biasing. So you write down. And so here we can use base resistor method. Write down that we can draw the circuit. Okay, tell me, this transistor is in which configuration? Common emitter or collector or base? I need the answer from both of you. It's okay if you are wrong, but I need a response from. Tell me this circuit is in which configuration? Common base configuration or common emitter configuration or common collector configuration? If it's common base configuration, you can just type base. That's enough. But I need a answer from both of you. එතකොට දැන් මට satisfaction එකක් එන්නේ මේ subject එක කොච්චරක් දුරට කියලා. guys මේ වැරදුනාට කමක් නැහැ. I got an answer from Sukira and Usman. Usman, are you there? Usman, I'm waiting for a response from you. No, I'm just asking to tell me whether this is in common configuration or emitter configuration or base configuration. I mean, which configuration it is. Okay, so here what you can do is you can check the input and output, right? So if you consider the input, this is the input circuit and this is the output circuit. So the input and output එකට මැද තියෙන මොකක්ද? IE. So this is the common emitter configuration, right? So this is common emitter configuration. So this is IB here, this is the then input, and this is out, this output circuit. So this common emitter. Okay, right. So here C1 and C2 capacitors are used to prevent bias current from traveling to input and output circuits. So only alternating voltage signals can travel through capacitors. So we don't need any currents to pass through, only the voltage varies accordingly. So for that only we have used capacitors. The circuit is totally fine if you don't use the capacitor source. So anyway, okay. So applying Kirchhoff's law, or else if you haven't studied Kirchhoff's law, we can just consider the total voltage here drops through the here, right? So first this one, the voltage drops here IBRB plus IBRE. So this is VBE. So here the voltage is VCC. That voltage drops across this resistor and across this barrier voltage. So VCC is equals to IBRB plus V. And VCC again I can write ICRC plus VCE. Okay. So you can write these two equations. So here VCC, a voltage here drops across this resistor and across this barrier voltage. And here we can consider 0 here, so it's ground, or otherwise it's relative to here. So VCC equals IBRB plus VBC, and then ICRC plus VCE, potential C related. And the next one, potential divider method. Okay, so first draw this and then I'll explain. Write down the topic potential divider. And you can draw this circuit. Now you may have studied in electricity, a series resistor system works as a potential divider, and parallel resistor system works as current divider. So here potential divider circuit means these R1, R2 resistors are working as a series resistor system. I'll explain more about it. First you finish drawing this. So here this circuit also common emitter, because you can see the emitter is common for both input circuit and for the output circuit. Okay. So here IB is very small, right? So therefore, the current, this IB is very small. Therefore, we can think the current coming here, I1, almost all current goes this way, right? In this circuit, we can think now actually this current I1 comes and divide as the IB and I2, right? But since IB is very small, we can consider I1 is approximately equal to I2. So the same, we can think the same current is passing through R1 and R2. So it is a series, right? If two resistors, uh, when two resistors, same current is passing through that, we know it's a series resistor, right? So then therefore we can consider think that R1 and R2 are series a resistor system. So therefore we can think they are potential dividers. Okay. So here as IB is very small, I1 is approximately equal to I2. Therefore R1 and R2 works as a potential divider. So R1 and R2 are series resistor system. Therefore now I can write I1 R1. Here the VCC is equals to I1 times R1. Here the potential drop we can calculate using Ohm's law. I1 R1 plus VBE plus IERB. Okay. And also then VB we can write VB is equals to VBE plus IER. Potential at A equals to this potential drop plus this potential drop. Okay, so with this we'll conclude the today's session, and in the next class we can discuss transistors characteristics and action of transistor, those things. And yeah, so I'll give you a break. We start the paper class at 10:15. So you can join at 15. So see you at